Okay, hi everybody. I'm Christos. I'm from Northwestern University. Thank you, Marco, for the introduction. And I'm going to tell you today about a project that I've been working on for the last 4 or 5 years, whose topic is a new method for evaluating what we call PL pragmatics. Okay? Of course, the first question should be, what do I mean by PL pragmatics? Often pragmatics is used to mean, pragmatic, but actually I have a more specific notion in mind. Okay? The idea of PL pragmatics actually goes way back in the world of programming languages. There is a seminal dissertation from 1968, Jim Morris's dissertation. It's in a context where people are still trying to understand what semantics means. So Jim Morris shows up and he says, we can borrow some ideas from the world of semiotics and linguistics. And if we want to talk about the various layers of programming languages, we can say that there is syntax, which is about the valid forms, what we can write down as valid programs. There is semantics, which is how these valid forms relate to each other and how they combine to give meaning to more complex forms. This is usually the intrinsic meaning of these forms that we can describe in the eternal language of mathematics. And then there is pragmatics, which is how the meaning of those words relates to the actual users. Something surprising happens after this analysis. In the next paragraph in the dissertation, Morris goes on to basically says, okay, we can reduce users to just the machine and what the machine observes. And here's the surprising part. He says, we don't need to care anymore about semantics. All we need to care is pragmatics, because all that matters is what the machine observes. And in the process, he basically equates pragmatics with operational semantics. From the perspective of semantics, this has a significant, it's a significant step, because he uses that as a building block to define what we call contextual equivalence, which has become the golden standard of understanding the meaning of programs and program fragments nowadays. But in terms of pragmatics, as I said, there is this reduction step. Basically, the user becomes the machine. Okay? In this talk, we are going to stick to semantics as being, the study of how we understand the meaning of pieces of programs, and also at the meta level, the properties of those programs, especially the theoretical ones, correctness and so on. But when it gets to pragmatics, we're going to take a more expansive view, again inspired by linguistics. In linguistics, the difference between semantics and pragmatics is that once you try to use a term in context, the context may modify the meaning of the term. And this is exactly what we're going to do for PL pragmatics. We are going to say that once you get a feature that has a specific semantics, when you place it in a work context, the value of that feature may change. Okay? And what I mean by work context, basically I mean things that we do as programmers and maintainers of programs, how easy it is to write code with particular features, how easy it is to debug it, and how easy it is to maintain it. Okay? And so on. So just to make things a little bit more concrete, a semantics question that we may want to examine is, how do, for instance, gradual type enforcement mechanisms work? What are their operations? What are their checks? What kind of error messages they give us when something goes wrong? Okay? A pragmatics question is, which of these mechanisms helps us, for instance, debug? Okay? By the way, if you have any questions, there is time at the end for questions, but I would prefer if we were a little bit more informal, so just let me know. Okay? Don't hesitate to interrupt. Cool. So now that we have PL pragmatics, I hope we are all on the same page about what PL pragmatics mean. Let's move to the how. We're going to do this empirically, okay? And just to exclude the obvious possibility, this is not a user studies method, okay? Instead, I am going to present the rational programmer, which is basically a recipe for constructing large-scale automated experiments that we can use to examine the validity, the answers to questions about pragmatics. Okay? So the first step in this recipe is that we pick a feature and some context to examine. Okay? Let's say, for instance, gradual typing and debugging. Those two go together all the time there needs to be a context when we're talking about pragmatics. Then what we do is we formulate a hypothesis. How is this feature going to benefit the developer in this particular context? This is a little bit vague, but the rational programmer actually asks us to do something a little bit more specific. It's not just about the how, we need to specify a use strategy. For instance, I'm going to use the gradual type system in a particular way in order to figure out where, let's say, a dynamic type violation, where is the root of such a violation. Okay? Once we have the use strategy, the next step is to turn it into an algorithmic procedure. Okay? This algorithmic procedure is actually the namesake rational programmer because it's an abstraction of a programmer working in that context to achieve a specific goal. Given this algorithmic procedure, we go and construct populations of scenario, let's say debugging scenario, for the particular running example of gradual typing and debugging. And then we can run a simulation. And from the data we get and we analyze, we can go back and examine our hypothesis whether we refute it or validate it. Okay? So, this is the pipeline. It's an instance of the scientific method, pretty much, with simulation at its core. I presented this as something that we can use. Oh, please stand behind the lectern. Sorry, I was moving too much. I presented this as something that we can use to examine a particular feature, but we can actually do the same for collections of features that have different semantics or even different features, as long as we are able to create multiple strategy variants, one for different features, so we can repeat this process in parallel, collect data, and compare the hypothesis for all the different features. Okay? I'll give you a more concrete example as we keep going. I want to say, though, that even though I made it look like a very streamlined process, there are significant challenges that someone needs to overcome in order to implement it. So we need to come up with a hypothesis, and in particular, a hypothesis that has a strategy at its core about how we are going to use the feature to achieve our goal. Then we need to turn this strategy into a procedure. And this is very tricky in some cases because we are abstracting over a programmer. This often involves creativity. So somehow we have to take that creativity out of the mix in order to get an actual algorithm. And finally, we need to be able to create a significant population, a diverse population of scenario, so that we can draw from the simulation results that have some significance too. Okay? So, and of course, all these answers to all these problems depend on the specifics. It's very specific to the question we ask. So every time someone tries to do a new rational programmer study, they have to try to understand how to overcome these obstacles. And this is where the research part of working with the rational programmer comes in. Cool. I'm going to make all of these things that I just said concrete, and I'm going to talk about the running question, about gradual typing and debugging, and in particular, which gradual type enforcement mechanisms help us with debugging. Okay? I'm going to open a parenthesis. By the way, before I get to the parenthesis, actually, this is work that I have been doing with my student, Lucas Lazarek, in collaboration with Ben Greenman and Matthias Pelaisen. It's a work in two parts, and actually, Lucas presented the second part of that work at ICFP earlier this work. In case some of you were there, I'm going to try to keep the overlap minimum, just to keep this talk self-contained. Lucas focused on the results and the data. I'm going to focus on the process. Okay? So, word scheme, so parentheses are okay. I'm going to open a parenthesis because I want to make sure that everybody is okay about what I mean about gradual typing enforcement mechanisms. Okay? And to do that, I'm going to talk about a small example. It's a simple example. We wrote an application. It consists of basically 3 different modules. One module is a library that we found, I don't know, somewhere in the Racket package system. Then we have a utils file that we also wrote. And finally, we have our main application file that uses the other 2. As we were working in this application, we noticed that we often do a bunch of silly mistakes, like passing the wrong kind of argument to a function. So we decided to take advantage of typed racket and its ability to basically add types gradually to programs, to add sort of some types to certain parts of our program. So we created a type interface between the library and the main, and we also fully typed our own utilities little module. Okay? Here is how roughly, I don't expect you to read the code. The important part here is that basically this is the library that we found somewhere in the package system, and this is the interface we wrote. Basically, the important part is that it says that we have a function exported JSON unpack that consumes JSON. It consumes a string and it gives us back a list of hash tables. Okay? What this guy does is reading the JSON object and then basically packaging it up iteratively in a list. Basically, it's a comprehension of a whole document. Our main file imports the interface so that it has access to the version of the library that is protected. And then it goes on to call JSON unpack with some file, and then calls also summarize edges that comes from our utilities library. Okay? Our utilities are fully written in typed racket. There are types to basically say that user info, which is the data that we have inside the JSON file, has been marshaled into a hash table, basically, and that summarize edges accepts a list of these user infos, a list of hash tables, and then it does some aggregation. Okay? So far, so good. We can ask the type checker of typed racket to inspect our program, analyze it, and it won't find any problem, because the way we use the types inside the typed module is consistent with the implementation of the code. However, what's going to happen afterwards when we try to run the program, even in typed racket, depends on the choice of the mechanism of enforcement we have made. Okay? And there are different answers on what should happen next. And the reason that there are the different answers is that actually our program, there is a problem with our program. When we created this interface and we said that the results needs to be a list of hash tables, we were not that careful. We basically looked at this function, made our assumptions, and we didn't pay attention actually to this little comment for the helper function that says that actually this one does not return a hash table, but returns an association list. Okay? So one answer about what should happen dynamically, which is the original answer about how we enforce types in gradual typing, it's what we call the natural semantics. Okay? So this natural semantics, what they do, every time there is a value flowing from typed code to untyped or from untyped to typed, they go and wrap that value. Okay? Usually, if it's a function, it creates a proxy function, and that proxy function intercepts arguments and results, checks that they are of the right kind, and then does the actual computation. This is the original implementation of gradual typing enforcement in typed racket, actually. And if we want to see what's going to happen, basically, the typed racket compiler is going to basically export this guy wrapped in a contract that basically enforces that type. So when we go inside our main file, our main module, and we try to call JSON pack, the contract will notice that the result is not a list of hash tables, and it's going to signal a dynamic violation of the type, and it's actually going to give us some help. It's going to give us a message that we call blame that points to the source of the problem. In this case, it has detected an inconsistency between the interface that we wrote and the actual implementation of the untyped library. Okay, great. This is very helpful. Now we know what the problem is. We can go fix it. Except that this kind of gradual typing that naturally permits, that's called sound gradual typing, if you Google it, you get really bad news. Okay, half of it is about death. Okay, and attempts to revive it. Okay, so, and there's a reason for that, right? We expect, as we're adding dynamic checks in our program, that things will start slowing down, okay? we also expect that if we add enough of those, maybe the runtime of the language will be able to take advantage of this extra typing information and do some optimizations, okay? The reality is that the slowdowns are so bad that sometimes you cannot use your program. And to make things even worse, how we can avoid these particular configurations, as we tell them of the as we call them, of the program, that do not exhibit these pathological slowdowns, is an open problem. Okay? There are a lot of options, a lot of things that we can do, a lot of different places we can go and add types, and knowing exactly where to invest our effort, we don't have any good guidance from tools or the language. Yes? It's you can. We will get to that later on. There is a benchmark shoot, the gradual typing benchmark shoot, and there is a paper called. Actually, I had it here. The eSound gradual typing dead paper that shows with very specific programs how things go really bad, really fast. Okay. Usually, it has to do with tight loops between an untyped and the typed module. What's happening in that case is that you go back and forth, accumulating more and more contracts, making the program more slow. There is some follow-up work by Robbie Findler and Dan Felty, one of his students, and Ben Greenman, where they show that you can collapse some of those, but it's not the general case. Okay? So, cool. Where were we? Here. So, in the face of this catastrophe of slowdowns, industry, the practitioners, decided to follow a completely different route. And they have what they call the erasure semantics. And what is the erasure semantics? Erasure semantics have other names, by the way. They are type hints, pluggable type systems. Gilad Prag has the plug from Newspeak from 2004. Type hints that exist even before that for Python. And it's actually the semantics that the most famous example of gradual typing in the world right now, the most widely used, uses TypeScript, okay? So what happens with the erasure semantics? We just forget the types, and TypeScript becomes JavaScript, okay? And of course, we have no penalty, okay? Cool, but let's see what this means in the case that we have actually a problem, okay? When we wrote our utilities code, we assumed that we're gonna be given hashes. But instead, we were given association lists. So when we actually try to get the hash out, we get an error, okay? It's an error that shows up deep inside our program. It has nothing to do with where the error was. And the only information that we get together with this error is basically a stack trace that says that this error, this dynamic error, happened inside this call of this function. Okay, we have to go and connect it actually with the source, which was the mistake in the interface. Cool. So, of course, academics didn't like that, so they tried to make a compromise between the expensiveness of the natural semantics and the everything goes situation of the erasure semantics. And there are many examples, but the one that we will consider today is the one called transient semantics, okay? That was first implemented as part of reticulated Python, but actually now typed racket, thanks to Ben Greenman, has also a transient backend. And what happens with the transient semantics is that we are not going to use proxies to protect values that go from one typed module to an untyped one and back and forth. Instead, we are going to rewrite our typed modules. And we're going to rewrite them in a way so that at every place where a problem may show up because of a mismatch, because we don't have something of the appropriate type, we have checks. So we are going to check that the argument comes from the appropriate constructor. In this case, that is a list. When we get stuff out of the list, we're going to check that they're hashes because we're expecting them to be hashes. When we get stuff out of the hashes, we're going to check that they're integers. Just like, so with a bunch of little diffused first order checks inside the program, we are trying to simulate the checks that the proxy will do, okay? And one of these checks in this particular situation is going to detect that actually we're not dealing with hashes, and it's going to give us a nice blame message, like before, in this particular case saying that there is this value that is coming from client, the main file that we have, does not match what this guy expects here according to its type. Okay? Again, notice that this blame information is a little bit different than what natural gave us. Natural, because it has these wrappers, it's able to connect it with the interface. Okay? So the summary of what I want to say is that basically I showed you a setup where we have a single syntax, a single type system, the type system of typed racket, which by the way, it's very close to the type system of TypeScript. Okay? But we have 3 different semantics and 3 error reporting mechanisms. So now that we have eliminated a bunch of variables about the setup of gradual typing mechanisms, we can go and refine our questions and our question about gradual typing and debugging. And basically, we can say which combination of semantics and errors helps us with debugging. Okay? So I'm closing the parenthesis, going back to the rational programmer. Okay? And now we will work through this pipeline, trying to create this experiment that will help us examine that question. Okay? So we start with the hypothesis. Remember, a hypothesis is valid in this world when it defines a strategy. Okay? So we need to develop a strategy as part of this hypothesis. Okay? The goal of the strategy is to take a debugging scenario, and the debugging scenario in this situation is basically some program that combines typed and untyped code and throws a dynamic error, and turn it into another program that does not exhibit a dynamic error, but some error that is some situation that helps us understand where the problem is. Okay? The root of the issue with the debugging scenario is that there is some inconsistency between the typed parts of the code and the untyped. Okay? The types and the implementation. And the reason figuring out where that root, the reason it's difficult to figure out where that root of the cause is because the code may show up inside untyped code. And untyped code may create values that may flow through the program until they hit a place where typed code tries to use them according to its assumptions and figure out that these assumptions do not hold. Okay? So one way we can start debugging such a program is basically to start adding more types. Because as we add more types, we will turn the inconsistency between types and implementation a problem that can be detected as the type checker works on typed code. Okay? Figuring out what type errors mean is not easy, but at least I claim here today that it's easier than trying to work with dynamic type errors. Okay? So from our perspective, what we're trying to do with our strategy here is we're going to use the error reports that we get together with the dynamic error, either the blame information or the stack trace, and try to ascend through this lattice of configurations on a gradual migration path. And our goal is to finish this search at a configuration that basically we have reduced the dynamic type error into a static one. Okay? In this case, if we've done that, we know exactly where to look for the inconsistency. It's the code that doesn't type check. Okay? Now, we call basically this strategy following the blame trail. And a strategy is successful if it manages to turn the debugging scenario into a one that exhibits the static type error. Okay? So, back to our example. If we consider that we are evaluating this example under the transient semantics, what happens is, as I said before, we're going to get a type error, a dynamic type error. Okay? This is going to point to the interface between client main and our utilities little library. So what we go and do is we type check, we add types to the main file because this is the untyped side of the boundary that was identified by blame. We run the program again. We get a new dynamic type error. This time, though, we have different information in the error message. This time, the mistake points to this boundary. So we go, we add types there, and we have reached our goal. Basically, we have detected the source of the error. Okay? At least at the module level. Everybody with me about this process? Okay? Let's see how this process fails under the erasure semantics. So what's happening is that we have client summarized that it's typed, okay? And we have this interface that is typed, but really nothing matters about the types when we're talking about how the program runs, okay? So we're going to get our exception that points inside the typed module. So it's not really, we cannot do anything. There is no pointer about where to add more types in our program. So we're literally stuck, okay? Cool. So now, through these steps, we have defined successfully our hypothesis. We say that if you give me two mechanisms, A and B, if I try A and B on the same pool of scenarios, and one of them is more successful than the other, then A offers more debugging facilities. Okay? Okay, so we've done that part. Let's go and try to target the middle parts of the pipeline, which is actually pretty challenging here. Why? First, for the strategy, the steps of adding types require human creativity, right? There is, as I said before, the problem of migrating code from untyped to typed, it's still open. We have some solutions that work with small programs, but not programs of any realistic size. Okay? The same is true about how we're going to construct a population. The instinctive thing to do here is to basically say, we are going to try and source programs from somewhere, I don't know, from GitHub. We're going to mine these programs. But when it comes to type errors, most of those do not survive testing. So they do not make it into public repositories. So we have to do something else. Okay? So I'm going to show you how we can deal with these two problems together at the same time. And in particular, we will start with the creation of our scenarios. Yes?
Quick one. There's also, I could also think about different quality of types that I might be adding to these modules. That's another axis.
That's another axis why it makes very hard to actually add types, where the human creativity comes in.
Should I be expecting some that we're going to be following a most specific type path for each module?
You will see in a bit. Okay. But that's an excellent observation. There are multiple types that you can add to a particular module, and this creates another dimension of why actually building an algorithmic strategy is tricky. Okay? Okay, so we will start with the problem of creating different scenarios first, because the way we will structure the solution to that problem is going to also help us turn the strategy into a procedure. Okay? So the idea we had is that instead of trying to find programs that already have problems, we can start with a collection of programs that have no problems, and then somehow turn them into many, many programs that have one problem that we know where it is. Okay? Lucky for us, there is a diverse collection of racket programs, the GTP programs, that are written from different people, from different purposes, for different purposes. They have different numbers of modules and so on. So along a number of metrics, you can say that it's a pretty interesting set of racket programs. And then we hope to turn those into a bunch of interesting debugging scenarios. So how we're going to do that? We're going to go back in time and look at mutation testing. Okay? So this is actually the first paper that introduced mutation testing. Does not exist. Everybody references it. We have tried to find it, but we cannot find it. It's not that. It was an undergrad, it was Dimoulas undergrad tech report. Okay? But it doesn't exist. We've searched. Okay? But then they published the paper, and what they describe in this paper is that basically what you can do is you can go to a program and change it slightly in one place, turn a plus to a minus. Okay? Small syntactic changes. They call these syntactic changes mutations. They call the means to introduce mutations the mutation operators. And these are basically, rewriting steps, very simple rewriting steps. The reason they develop mutation is to evaluate testing suits. So what you do is you have your testing suite, you get your program, you mutate your program, you get thousands of mutants, as they called. If your testing suite is good, it must kill all the mutants, okay? As long as they are non-equivalent semantically to the original program, okay? when they do mutation, they care a lot about introducing little syntactic differences that cause significant behavioral differences, deep bugs. This is not the setting that we are in, okay? Because we want to introduce type-level mistakes, okay? Like this one, for instance, where somewhere inside the implementation, this function is returning an association list, and instead, we have an annotation that says that the function returns a hash, okay? So there are two ways we can actually go and do that, okay? The first way is we can say, okay, the annotation is correct, completely ignore this comment, the comment is correct, the original program, the correct program, had a hash here, okay? So if we want to turn this program into a buggy one, we can go and replace the hash with a cons. Okay? This is what we call a type-level code mutation. It's type-level because it can be detected by the gradual type system or from the type checker if the module is typed. Okay? There's an alternative. We can say, oh, okay, the original program had association lists everywhere, and this should be the correct type. So if we want to create a discrepancy, what we can go is go and change the type. And this introduces a second type of mutations that we call type interface mutations. Okay? So basically, by working with the grammar of the program and the grammar of types, we get different simple rewriting rules that we can apply to inject bugs into our program. I lied a little bit. The interface mutators need a little bit more work. And I'm going to show you why. Let's say that we did the type interface mutation where basically we turn the association type into hash. The client that ends up transitively using this code, if we started with a correct program, does not care that we actually have changed the type. It has an association operation there. So the mistake is never going to show up unless if we have types all over the place. What we need to do to make the mistake manifest at runtime is that we also need to go and update the client. And this is a very big problem, of course, because you have to chase down all uses of this data wherever it flows in the program and try to modify, do all the mutations at the right place. So we took a leaf out of the gradual type book, and what we did instead, we modified the values, not the places where they are used. We created adapters around them so that they flow where they have to go, and when they are used, then they blow up. Okay? Okay, so we apply our mutators to the GTP benchmarks, we get millions of scenarios. We have to ask, are they any good? We need to make sure that these mutators introduce type mistakes in a way that covers a wide range of type mistakes that looks like something that people do. Okay? We need to get different representation of equal representation of all the programs that we had. We don't want the mutators to be dominated by a single program. Okay? So at the end, if we want to argue that we have an adequate population, we need to go and analyze those mutants empirically again, look at them, perform some statistical analysis to make sure that we get interesting, non-trivial debugging scenarios of sufficient diversity. Okay? We were lucky in this particular case, but this is also, and actually we confirmed that we can get more than 1 million interesting scenarios at the end that are basically interesting. Okay? But in general, this is a step that needs a little bit of care when someone is working with the rational programmer method. Okay? Because the results that we get at the end and the conclusions that we draw are as good as the population that we work with. Okay, cool. So now that we have our population down, we can go and talk about the strategy. So in order to turn the strategy into a procedure, we need to do two things. Starting from a debugging scenario, we have to decide where to go next, and we have to decide what types to add. Okay, and we already talked about how difficult the type situation is. It turns out from the two, actually, the types is the most difficult. the error reporting messages that we get back help us determine where to look next. We can algorithmically look at blame messages, decide which component they ask us to go and modify. We can do the same thing with stack traces. Let's say pick the top frame or the bottom frame or one of those, and then isolate a component from that information that is the next that we need to add types. Okay? Lucky for us, the way we construct populations, it's as easy to add types to the programs. Why? Because the GTP programs come actually with types for all their components. Every component has two versions, a typed and an untyped. And those types are written by humans, okay? And we know that they are correct with respect to the implementation. So what we have to do as we go up this migratory lattice is basically we have to go and swap the component we identified from an untyped version and bring in its typed version. Okay? Make sense? Cool. Okay, so now we are ready to simulate the rational programmer finally. We need to do a little bit of sampling. We have way too many mutants. We ended up sampling with some reasonable way so that we get preserve the diversity of the whole population. We ended up going with 100K debugging scenarios, a good number, okay? About 70 for code bugs and 30 for interface bugs. Okay? I want to say a little bit more because it's not what I have hidden a detail here. We don't have a single rational programmer. We actually have 3 variants, okay? Because we have 3 different semantics here that we are dealing with. And in fact, we don't have 3, we have 4, okay? Because blame in transient blames potentially multiple components. So in order to isolate the error information that we're gonna follow one of those, okay? So we have 2 different ways. We either pick the oldest one, which is akin to saying we're trying to go towards the earliest occurrence of the manifestation of the bug, or the latest one, which is basically we are treating the blame information the same way we will treat a stack. Okay? And there is another issue that adds a little bit more complexity. These 3 now rational programmers mix 2 different things together. They do both checking that Erasure doesn't do, and they have also an error reporting mechanism. So maybe, since we're doing this experiment to understand and analyze how these mechanisms help programmers debug, maybe we should separate their effects, okay? Lucky for us, we can easily do it in the rational programmer framework because we can create more variants of the rational programmer. So in addition to those that we have here, we created another 2. Those are just like the natural and transient semantics, but they do not follow blame. They ignore blame, and they just follow the stack trace from the exception that you get from the dynamic checks that those semantics perform. Okay? Which means that any difference in terms of data and validity of the hypothesis we're going to see about these guys and these guys up here will tell us something about how useful blame itself is for its mechanism. Okay? So they act as baselines for blame. Okay? Okay? So now with everything in hand, we can go run a massive experiment. I think it runs for at least 2 weeks on our to run everything on our big cluster that we have at Northwestern. And after that, we collect a bunch of data and we analyze it. Okay? So I'm going to show you a little bit of the data that we've seen. Lucas talked on Thursday a little bit more extensively about that. I want to show you data that confirms something we were suspecting and data that confirms that revealed something that we didn't expect. Okay? So about the thing we were suspecting, we were expecting that since natural uses properties that connect the location, the types with the place where the typed values are used and vice versa, natural will outperform every other semantics, okay? And this is what this shows. Basically, it's a head-to-head comparison between natural and every other rational programmer we have. Here on the x-axis, we have the various versions of the rational programmer. This is green, meaning that basically for 15% of the scenarios, natural outperforms the natural exceptions. There is no red because there is no scenario where natural exceptions outperforms natural. Okay, so you see green across the board. You can see that the results are a little bit more moderate when we are dealing with code bugs. Okay, the maximum difference, for instance, between the difference between erasure and natural is about 11%, and down with transient it goes to 4%. The results are much more impressive when we are looking to interface bugs, where the difference with erasure goes to above 20%. Okay? Now the surprising part. I talked about these baselines for blame. If we try to see how those rational programmers compare to every other mode, it's abysmal. They do really, really bad. So which says that basically if you take from gradual typing blame, and all these checks actually that we have are there just for debugging, if you take blame, then basically we negate the benefits of sound gradual typing. Okay? So, what we learned? Two things. Natural blame is the most useful in terms of debugging. Checking without blame is subpar. I want to say that this second point is also interesting for another reason. If you open any theoretical paper about gradual typing, most of the times blame is excluded. Okay? There is a third point that I want to make, and this has to do with how bad is the performance of sound gradual typing. We try to look not only at how useful these semantics are to help you debug bugs, but also if they detect the problems. Two different things. Do they raise an error, or is the information useful so that we can go and find the error? And then when we collected that data from our experiment, we saw that the erasure, the one that doesn't check anything, the cheapest one, detects approximately the same number of bugs as the other ones that do the expensive checks. Okay? Of course, I have to say that this is an experiment, so we have to be clear that there are threats to validity. Okay? This is all done in the context of typed racket. If you go to a language with a different runtime, the experiment cannot generalize there. It needs to be repeated. It's about the particular type system. It's about the particular population of programs. So with a little bit of salt in what I say, I think that we have some evidence that says that a language designer who wants to add a gradual type system to their language, maybe they should consider erasure for production, okay? And then use blame and natural semantics as a debugging mechanism, as an alternative semantics to try to get more information and work offline with their program. Okay? Now, I want to take in the last few minutes a step back and talk a little bit about the big picture besides the rational programmer, and in particular, why we call this rational. Okay? So, the reason we call it the introduction of rationality in science goes way, way back. Okay? One notable point is John Stuart Mill and his idea that later was called Homo economicus. Okay? He didn't name that. Studies of Mill's work basically called it the Homo economicus. The idea there is that if you want to understand how humans behave, you should create a rational abstraction. Rational means they try to maximize their benefit, okay, in some situation, and put them in a setting where if you try to understand how different economic agents interact, all you have to do is to try to figure out how they can reach a balance between their interests in that setting, okay? This idea has seen many interpretations, many uses. It has been abused heavily. It has also influenced significantly the study of game theory and CS economics to get combined with Bayesian statistics. Okay? The one that is more closer to the rational programmer is some ideas by Herbert Simon about bounded rationality, where basically it's a criticism to the original ideas of rationality by Stuart Mill, where Simon basically said that, you know, humans they're not omnipotent beings. They cannot consider, you know, optimal solutions at any point. Instead, they're trying to find a solution that satisfies, and he introduced that work, their goals. So it may not be the optimal choice at the current point, but it's good enough. And exactly that's what we try to reproduce with the rational programmer. Of course, all of this work has mathematical underpinnings and statistics and decision theory and so on. We don't do the same. The connection is at the metaphor level at this point. Okay? But the real reason I mention all this is because I want to say that we shouldn't confuse the rational programmer with a real programmer. It's a strategic simplification so that we can do an experiment. Okay? Exactly what the rational programmer is, it's a device for figuring out connections between the design and the semantics of the programming language and the benefits that it can offer in a particular context. It does not mean that if we take humans out of the street and ask them to repeat this process that they will be able to repeat it or that they will choose to repeat it. The questions that we ask with the rational programmer are questions of what we defined as PL pragmatics. They are not questions of usability or human-computer interaction. Okay? The interesting thing, though, is that now we have some way to connect actually the semantics of the programming languages with bigger picture uses of the same features of the programming language and do apples-to-apples comparisons. So far what we've done with it, I talked today about the middle bullet. Before that, Lucas, my student, had also worked out how we can debug with contracts logical mistakes. And we have an upcoming paper at UPSLA where we look how profilers can help us navigate type, what profiling strategies we can use to figure out which place to go next in the migration lattice to avoid slowdowns. Okay? And I'm going to conclude here and open the floor to questions. I just want to say that it's not just me. Besides Lucas, Matthias, and Ben that I have already mentioned, Alexis King, Robbie Findler, and Kaspar Popova have been part of this adventure of the rational programmer. Thank you.
So, open to questions.
I have a question about heuristics. Have you been able to come up with some kinds of heuristics that help you sort of monotonically increase or make your way towards the goal through that lattice?
That's an excellent question. So actually, we looked in this. We looked exactly into this topic with our first paper, not for gradual types, but we looked how contracts, following blame for contracts, whether it gets you closer to the goal. Okay, and it's very surprising. In most scenarios, it does. The strategy of following the blame, but there is a very weird corner case in the implementation of Racket's contract system that violates this monotonicity. And here is what's happening. So it has to do with the interaction between state, hidden state that the runtime uses, and the contract system. So what's happening is when you hash a value, there is some hidden state that generates the keys, okay? And then iteration over hashes depends on those keys, which are, this counter. So if you write a contract, like the ones that we wrote, that were extremely precise, that were actually adding values to sets, which are implemented underneath with hashes, in order to check set properties, you change the value of the counter. So just adding the contract interferes with the actual behavior of the program, causing different contracts to fire up, depending on what contracts you have in the program. Which means you may add a contract, expect that you will get closer, but all of a sudden a different error shows up that gets you further away. Okay? We haven't found something similar with the gradual typing, and the reason for that is that it's very hard to instrument Racket's runtime in order with proxies, the way we try to do it, to get information. In fact, it was Alexis, when she was at Northwestern, basically worked on building for us and the infrastructure that we needed for that experiment. Yeah.
Thank you. Wonderful talk. We started this discussion looking at a language with the same syntax, the same language, same syntax, and 3 different semantics. I'm interested in investigating teaching language progressions and afraid of doing user studies. So It seems like the rational programmer might also be applicable to different related languages.
Exactly.
That have chained on. Okay, cool.
I haven't tried it, so I cannot say, but I believe that it's doable.
Cool.
Okay? I don't want to say something now, that later on.
I won't hold you to it.
Yes. Yeah. Okay.
I'll try to ask a question. So it seems like the idea of blame is like a single point. And oftentimes it seems when you really have real problems, it's not one point, but it might be two or three or a pathway. Is that a valid idea? And I'm thinking about, oftentimes programmers will talk about a smell. This smells funny. I'm wondering if there's something there that, to give the idea that there are areas that are more suspicious than others.
Yeah, so you're absolutely right. Blame points to a single place in the code. And in fact, as this experiment show with data, we knew that in a theoretical and anecdotal level before, but now we have data. Blame does not point you directly to where the problem is. You may have to do a transformation, chase blame a little bit, chase it again and again and again until you get to the blame. So there is a question whether we could have provided that information from the beginning and give basically a trail through the program of changes, or identify the most problematic piece of code and so on. Yeah, you are absolutely right. We haven't done that. I don't have any idea how to do it. But yes, blame is not the location of an error. Yeah.
So if you wanted to move to satisficing and incorporate that into your framework, do you have an idea how you would do that?
We already implement this a little bit very precise, but we are already inspired by bounded rationality. I think the idea of the optimal rational programmer is unrealistic, because we don't, if I see an error, the optimal choice is to go as close to the error as I can, right? So that's why the rational programmers we construct are already bounded, in the sense that they are trying to go to maximize what they can do with the information they are given without looking for tools outside the feature that they are working. For instance, we don't look at some extra debugging tool that we may have and so on. We just look at the type system, and we're trying to make a choice that may not be the best, but at the moment, with the information we have, we hope that, and the experiment confirms, it gets us towards a solution. Yeah.
So I don't know if you've seen, you have thought about this idea before, but would this work, for example, to verify a communication protocol between components that are distributed?
Yes. I don't know how to do it. I expect that the undertaking of constructing an infrastructure where we can perform this kind of... So, for instance, Lucas, my student, has spent more than a year on just building the infrastructure for running the experiment. And he had to do it twice. We don't know yet how to generalize the infrastructure that we have. He had to do it twice for the 2 ICFP papers and once more. So basically he spent his whole PhD on building infrastructure in order to do the measurements, okay? So I don't know how hard and how time consuming and how difficult it is to construct something like that for a distributed system. And there is also, I don't know how, it's an open question, how we can actually create scenario. Because mutation was something that was around. I'm not sure if there is something similar when it gets to basically trying to break down different, to do things to violate protocols and then see how easy it is to find them.
Yeah, so I've had this discussion with Matthias before.
Okay.
So it's really, I'll give you a very specific context, right? So I teach CS1 students how to do distributed programming. And of course, some of the nastiest bugs are the ones where the communication protocol is violated.
Yes.
Right? And
yes.
so the question is now, how do we pin that down, right?
Yes.
So it would be a wonderful case study, right? If you ever come around to figuring this out.
Yeah, yeah. By the way, it's some work by Cameron Moy and Matthias on something called trace contracts, which are contracts for basically observing sequences of interactions and can be to observe protocols. And it comes with blame. And of course, it's an open question how useful that blame is.
Yep.
I want to say something that I forgot. I said that the rational programmer is not about humans directly, but we learn strategies, okay, that work, and we have hard evidence that they work in certain cases. So we can use this knowledge to explain the benefits to students and then teach them the strategies. Okay, so for instance, my PL course at Northwestern, the last week is spent on what we call Pragmatics, where basically the students come in the class and they basically perform rational programmer-like exercises. Okay? Yeah, sorry. Thank you.